March 4th, 1944. 8th Air Force Headquarters, High Wycombe, England. The mission board shows Berlin, and for the first time in aviation history, single-engine American fighters will escort bombers all the way to the German capital and back. 662 miles each direction, 1,324 miles round trip. Impossible range for any fighter that exists, except the pilots climbing into their cockpits this morning know something the Luftwaffe doesn't. Their P-51 Mustangs carry fuel in places no fighter was designed to carry it. 85 gallons sloshing directly behind the pilot's seat in a tank that makes the aircraft handle like a drunk elephant on takeoff. Another 184 gallons split between the wings, plus 2 external tanks under the wings holding another 150 gallons that will be dropped somewhere over the North Sea. The fuel load alone weighs nearly 3,000 pounds, more than the engine, more than the airframe. The pilots call it flying a bomb with wings, and they're not entirely wrong. But that's not even the dangerous part. The dangerous part is what's in the fuel. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The standard aviation gasoline everyone's been using since 1940 is rated 100/130 octane. A miracle fuel in its own right, developed after years of research and millions in investment. It transformed air combat over Britain, gave Spitfires and Hurricanes the power to match German fighters at altitude, single-handedly saved the Royal Air Force during the Battle of Britain. But by 1944, it's not enough. The war has moved. The bombers need to reach targets deep in Germany, and fighters need to go with them. Range matters more than speed now. Endurance matters more than climb rate. And someone, somewhere in the vast machinery of the Allied war effort, developed a fuel so potent it violates every safety regulation written. They're calling it Grade 100/150. The 100 refers to the lean mixture octane rating. The 150 refers to the rich mixture performance number. That second number doesn't even exist on the standard octane scale, which only goes to 100. Performance numbers above 100 measure fuel, mixed with tetraethyl lead at concentrations that would be considered poisonous waste in peacetime. The stuff eats rubber. Contact with synthetic rubber seals, gaskets, and fuel lines causes deterioration so rapid that maintenance crews have to replace parts on shortened schedules or risk catastrophic leaks mid-flight. The lead content is so high that ground crews handling it are issued warnings about toxicity. Spills on skin cause chemical burns. Fumes cause nausea and disorientation. Every barrel comes with handling instructions written, in the kind of bureaucratic terror that suggests lawyers were involved. But here's what it does to an engine. The Packard V1650 Merlin installed in every P-51 Mustang is rated for 18 pounds of boost pressure per square inch, using standard 130 octane fuel. That gives you about 1,400 horsepower at critical altitude, war emergency power for brief periods. With 150 octane fuel, you can push manifold pressure to 25 pounds per square inch, 75 inches of mercury on the gauge. The engine doesn't just accept this insane pressure, it thrives on it. Horsepower jumps from 1,400 to nearly 1,800. That's almost 30% more power from the same engine. No mechanical modifications required, just different fuel. The performance gains are staggering. A P-51B on standard fuel cruises at 280 miles per hour at 25,000 feet. Same aircraft on 150 octane cruises at 300 miles per hour, 20 more miles per hour just from the fuel. At sea level, which matters for catching German Von buzz bombs launched at London, the speed increase is even more dramatic. 368 miles per hour with standard fuel, 382 miles per hour with 150 octane. But speed isn't why they're using it today. Range is. Higher octane fuel doesn't just make engines more powerful, it makes them more efficient at cruise settings. The Merlin engine burning 150 octane fuel at optimal cruise power consumes approximately 58 gallons per hour. Same engine on standard fuel burns 65 gallons per hour. That 7-gallon per hour difference might not sound significant until you multiply it across a 5-hour mission. 35 fewer gallons consumed means 35 more gallons available for range. At cruise speed, that's an extra hour and 15 minutes in the air, an extra 350 miles of combat radius. The difference between turning back at the German border and escorting bombers all the way to Berlin. The fuel arrived in England throughout the winter of 1943 to 1944, not in large quantities, not with official fanfare. The logistics were nightmare. Every gallon had to be shipped across the Atlantic in tankers running the U-boat gauntlet, then distributed to forward airfields through supply chains designed for different specifications. Purple dyed instead of the green of standard 130 octane. Easy to distinguish, impossible to mix without contamination. 8th Air Force Fighter Command sent requests in May 1944 asking for immediate supply of grade 150 fuel for P-47, P-51 and P-38 aircraft. They'd run successful service tests at Wright Field and Eglin Field. The engineering data was conclusive. The performance gains were measurable and dramatic. But implementing it in combat squadrons required retraining every pilot, every crew chief, every mechanic who touched an aircraft. Because here's the thing nobody tells you about high-performance fuel in a high-performance fighter. It doesn't just make the plane faster. It makes it different. The P-51 Mustang with that 85-gallon fuselage tank already handles like a pig on takeoff. The center of gravity sits too far aft when the tank is full. The aircraft wants to tip nose up, wants to stall before reaching flying speed. Pilots learn to use all available runway, keep the stick forward during the takeoff roll, rotate carefully and pray nothing goes wrong before they burn through 30 gallons and bring the CG forward into acceptable range. Now add 150 octane fuel and the extra power it produces. The engine develops torque the airframe wasn't originally designed to handle. During takeoff with the fuselage tank full and war emergency power engaged, the aircraft tries to roll left from propeller torque with enough force to flip you inverted if you're not paying attention. Right rudder, lots of it, constant forward stick pressure, delicate control inputs, while nursing a fully loaded fighter into the air, with barely enough runway and one mistake away from a smoking hole in the English countryside. The training is extensive and specific. Pilots receive detailed briefings on fuel management. You start on the fuselage tank because you need to empty it first. 85 gallons behind your back, making the aircraft unstable, turning every maneuver into a test of pilot skill. You burn that tank dry before crossing the channel. By the time you reach hostile airspace, the CG has moved forward, the handling has improved, and you can actually fight if German fighters show up. Then you switch to the external drop tanks, 2 big metal eggs under your wings, 75 gallons each for a total of 150 gallons of additional range. You run of those tanks until they're empty or until bandits appear, whichever comes first. German fighters love attacking bombers during the escort handoff, that vulnerable moment when short-range fighters turn for home and long-range escorts haven't arrived yet. If you're still carrying drop tanks when the shooting starts, you jettison them immediately. The weight penalty and drag penalty make dogfighting impossible. Only after dropping externals do you switch to the wing tanks. 184 gallons total, 92 per side. Fuel that's been there since England but couldn't be used earlier because of the fuel management sequence. This is your fighting fuel, the fuel you'll use for combat and for the flight home. And if you've managed everything correctly, if you haven't had to push war emergency power to escape a fighter, if you haven't had to dogfight burning fuel at 250 gallons per hour, you'll have enough to make it back to England. March 4th, 1944. The bombers are wheels up first. B-17 Flying Fortresses and B-24 Liberators, hundreds of them, forming up over England in combat boxes that take an hour to assemble. Each bomber carries maximum fuel, maximum bomb load, and maximum crew anxiety about what's waiting over the target. Then, the fighters launch. P-51 Mustangs from the 357th Fighter Group, the 354th Fighter Group, the 356th Fighter Group. More squadrons joining as the mission progresses. each pilot going through the mental checklist that keeps him alive. Fuel selector to fuselage tank, mixture to auto-rich, propeller to full increase RPM, throttle forward to 75 inches manifold pressure, right rudder to counter torque, stick forward to keep the tail down. The aircraft lumber into the air like overloaded trucks, not the nimble fighters they'll become once the fuel burns off. Some pilots barely clear the trees at the end of the runway. Others abort when an engine coughs or a gauge shows abnormal readings. Better to scrub the mission than attempt a 6-hour flight with questionable equipment. The ones who make it airborne begin the long climb to altitude, 25,000 feet, where the bombers cruise and where the Merlin engine's 2-stage supercharger provides maximum efficiency. The fuselage tank empties during this climb, 85 gallons, transforming unstable handling into something manageable. By the time they cross the English coast heading east, the Mustangs are fighters again, not fuel tankers pretending to be aircraft. The North Sea below is grey and cold and infinite. Pilots check their fuel gauges obsessively. Fuel flow, fuel pressure, fuel quantity. The numbers have to match the mission profile or you're swimming home. Nobody talks about ditching in the North Sea. Water temperature hovers just above freezing. Survival time measured in minutes. The air-sea rescue launches occasionally fish out downed pilots, but mostly they fish out bodies. Holland appears on the horizon. Occupied territory, German radar tracking every aircraft, flak batteries waiting for anything that strays too low. The Mustangs stay high, stay with the bombers, scanning the sky for the black dots that mean German fighters inbound. And this is where the fuel, the dangerous fuel, the 150-octane fuel that violates safety regulations and requires toxic handling procedures, this is where it proves its worth. Because when the Luftwaffe arrives, and they will arrive, the Mustangs can fight without worrying about fuel state. They have enough. For the first time in the air war over Europe, American escort fighters have enough fuel to fight deep in German territory and still make it home. The mission profile called for penetration to Berlin, escort the bombers to the target, protect them during the bomb run when they're straight and level and vulnerable, then shepherd them out of German airspace and back, across the Channel. 662 miles each way, 1,324 total, plus combat, plus manoeuvring, plus whatever contingencies develop when people are shooting at you. It's March 4th, 1944, and the 8th Air Force is about to prove something the Germans thought impossible. Single-engine fighters escorting bombers to Berlin and back, not twin-engine P-38s with their dual redundancy. Single-engine P-51s with their efficient Merlins and their dangerous fuel, and their pilots who've learned to manage fuel like accountants manage ledgers. But this story doesn't start in March 1944 over Germany. It starts 2 years earlier in California, in an engineering office at North American Aviation, where someone made a decision that would change everything. July 1943. North American Aviation's plant in Inglewood, California, the manufacturing heart that's churning out P-51 Mustangs faster than the military can figure out what to do with them. The engineering department receives a directive from the U.S. Army Air Forces. Maximize internal fuel capacity on all fighter aircraft. Immediate priority. The directive doesn't explain why, but the implications are obvious. The bomber offensive against Germany is failing, not tactically, strategically. 8 Air Force is losing bombers faster than factories can replace them. The problem isn't German flak, it's German fighters. Messerschmitt Bf 109s and Focke-Wulf 190 fighters that wait just beyond the range of American escort fighters, then tear into the bomber formations like wolves into sheep. P-47 Thunderbolts, the primary escort fighter in 1943, have combat radius of about 230 miles with external tanks. They can escort bombers to the German border, maybe slightly beyond if everything goes perfectly. Then they have to turn for home, leaving the bombers naked for the next 500 miles into Germany and 500 miles back out. The mathematics are brutal. Without escort, bomber losses run between 8 and 12% per mission. That's not sustainable. A bomber crew's tour of duty is 25 missions. If you're losing 10% per mission, the statistical probability of completing a tour drops below 10%. You're asking men to fly into near certain death. And even in war, even with everything at stake, there are limits. So, the directive goes out. Maximize fuel capacity. Figure out how to make fighters go farther. And at North American Aviation, the engineering team looks at the P-51 and sees potential. The Mustang already carries more fuel than comparable fighters. 184 gallons split between two wing tanks, 92 gallons each, sitting between the forward and aft wing spars. That design choice, made back in 1940 when the aircraft was first developed for the British, gives the Mustang inherent range advantage. Most fighters carry fuel in the fuselage. The Mustang carries it in the wings, and that leaves fuselage space available for other things, like maybe, just maybe, another fuel tank. The engineering team runs calculations. The P-51B, with its Packard-built Merlin V1650 engine, weighs about 7,000 pounds empty. Maximum takeoff weight is around 11,000 pounds with external stores. That leaves approximately 4,000 pounds for fuel, ammunition, pilot, and equipment. Fuel at £6 per gallon means the existing 184 gallons weighs about 1,100 pounds. Add 85 more gallons, and you're adding another 510 pounds. The weight isn't the problem, the location is. Put a fuel tank behind the pilot, directly behind the cockpit where the radio equipment currently sits, and you're adding 500 pounds aft of the centre of gravity. The CG moves backward, not slightly, dramatically. Enough to make the aircraft dangerously unstable during takeoff and landing when the tank is full. But here's what the engineers notice. When they switched from the Allison engine to the heavier Merlin, they had to move the wing slightly forward to maintain CG balance. The Merlin weighs 350 pounds more than the Allison. That forward wing movement compensated for the engine weight, but it also moved the CG forward enough that there might, just possibly, be margin to add fuel behind the pilot without pushing the CG beyond acceptable limits. Might, possibly. These are not words engineers like using when discussing aircraft stability. But it's July 1943, and the directive is clear: maximize fuel capacity. So they design the tank. 85 gallons of rubber bladder fuel cell, self-sealing like all combat aircraft fuel tanks, fitted into the fuselage space behind the pilot's armor plate. The radio equipment gets relocated. Some of it moves forward. Some of it gets smaller, thanks to improving electronics. Some of it just gets removed because range matters more than communication. Testing begins in August. A P-51B gets modified with the fuselage tank at Wright Field in Ohio, where the Army Air Forces runs its technical evaluation programs. Test pilots fly it carefully, conservatively, documenting every handling characteristic. The report, filed in September 1943, is not encouraging. The test report from Wright Field lands on desks at North American Aviation like a grenade. Longitudinal stability with full fuselage tank is marginal at best and dangerous at worst. Aircraft exhibits strong nose-up tendency during takeoff. Stall characteristics deteriorate significantly. Recovery from spins becomes problematic. Not recommended for operational use without significant airframe modifications. In other words, the 85-gallon fuselage tank makes the Mustang want to kill its pilot. The engineering team reads the report and faces a choice that will echo through aviation history. They can abandon the fuselage tank concept, keep the P-51 as a short to medium-range fighter, and watch the bomber offensive continue to bleed. Or they can fix it. Not fix the stability problem. That's physics. You can't move 510 pounds aft of the centre of gravity without consequences. But you can fix how pilots manage those consequences. The solution is elegant in its simplicity and terrifying in its execution. You don't fly the aircraft with a full fuselage tank. You burn the fuselage tank first. During takeoff and climb, before entering combat, you run that dangerous fuel through the engine and use it up. The centre of gravity moves forward as the tank empties. By the time you reach altitude and cross into hostile territory, the fuselage tank is dry, The CG is back in acceptable range, and the aircraft handles normally. It requires discipline. Fuel management becomes sacred ritual. Every pilot memorizes the sequence. Fuselage tank for takeoff and climb. External drop tanks for cruise to target. Wing tanks for combat and return. Deviate from this sequence and you're fighting German fighters in an aircraft that handles like a brick with wings, or you're attempting to land with 500 pounds too far aft and discovering that a perfectly good fighter can become a lawn dart in the span of 3 seconds. North American Aviation publishes Technical Order 01-60J-26 in October 1943. Operation of P-51 series airplanes with 85-gallon fuselage fuel tank. 23 pages of detailed procedures, warnings, limitations, and consequences. The warnings are numerous and dire. Do not attempt aerobatic maneuvers with fuselage tank containing more than 30 gallons. Do not engage in combat with fuselage tank containing more than 20 gallons. Takeoff with full fuselage. Tank requires minimum runway length of 5,000 feet. Landing with more than 40 gallons in fuselage tank is prohibited except in emergency. The limitations mean that combat squadrons receiving P-51Bs with fuselage tanks need complete retraining. Everything pilots thought they knew about the Mustang changes when that tank gets installed. The aircraft you take off in is different from the aircraft you fight in, which is different from the aircraft you land in. 3 distinct handling regimes in one airframe, and switching between them happens while you're flying over enemy territory with people shooting at you. By November 1943, P-51Bs with fuselage tanks begin arriving in England. The 354th Fighter Group receives them first. Pilots familiar with the earlier Mustangs, aircraft that handled beautifully in all regimes, suddenly face fighters that require constant attention to fuel state and CG position. The learning curve is steep and occasionally fatal. A pilot forgets to switch from fuselage to external tanks, enters combat with the CG too far aft, attempts a hard turn to evade a Bf-109, and discovers the aircraft won't respond. The Mustang departs controlled flight, enters an inverted spin, and impacts German farmland at terminal velocity. Another pilot burns the fuselage tank properly but mismanages the external tanks, drops them while they still contain 60 gallons, and runs out of fuel 40 miles from England. He glides the Mustang down through 10,000 feet, 8,000, 5,000, looking for any flat space to dead stick a landing. He doesn't find one. The North Sea claims another pilot, another aircraft, another data point in the learning process. But the pilots who master the system, who memorize the fuel sequence and respect the limitations and treat the fuselage tank like the dangerous compromise it represents, those pilots discover something extraordinary. The P-51B with fuselage tank and external drops has combat radius, approaching 750 miles. That's nearly 3 times the range of a P-47 Thunderbolt. It's enough to escort bombers deep into Germany. Not quite to Berlin, not yet, but deeper than any single-engine fighter has ever gone. December 1943. The 354th Fighter Group flies its first long-range escort mission. The target is Kiel on the Baltic coast, 400 miles from England. The Mustangs carry full fuel loads, 85 gallons in the fuselage tank, 184 in the wings, 150 in external drops. Total fuel capacity 419 gallons. The mission is successful. The bombers hit the target, the Mustangs provide continuous escort, and German fighters, accustomed to attacking bombers after the short-range escorts turn for home, find themselves engaging P-51s 300 miles inside Germany. The psychology of the air war shifts. The Luftwaffe can no longer wait for the escorts to leave. The escorts aren't leaving. But 750 miles of combat radius still isn't enough for Berlin. The German capital sits 662 miles from England. You need at least 700 miles of combat radius, preferably 800 to account for combat maneuvering and contingencies. The P-51 with 85-gallon fuselage tank gets close, but close doesn't win wars. Then the fuel changes everything. The development of 150-octane aviation fuel didn't happen overnight. It didn't happen because one mechanic mixed chemicals in a workshop. It happened through systematic industrial research, spanning years and involving hundreds of chemists, engineers, and test pilots. The story begins in the 1930s with a former Army pilot turned oil company executive named James Doolittle. Yes, that Doolittle, the same man who would later lead the famous raid on Tokyo in April 1942. But in the 1930s, Lieutenant Colonel Doolittle worked for Shell Oil Company, and he had a vision. Aircraft engines operated under a fundamental limitation called detonation, also known as knock. Fuel-air mixture in the cylinder is supposed to burn smoothly when ignited by the spark plug, creating steady pressure that pushes the piston down. But under high compression or high temperatures, the mixture can spontaneously explode before the spark plug fires. This premature detonation creates shock waves that damage pistons, crack cylinder heads, and destroy engines. Octane rating measures fuel's resistance to detonation. Higher octane means higher compression ratios without knock. Higher compression ratios mean more power from the same displacement. In the 1930s, automotive gasoline rated around 70 to 80 octane. Aviation fuel, which needed to be better because aircraft engines couldn't afford to fail, rated around 87 octane. Doolittle understood that engine development was limited by fuel availability. Engine manufacturers wouldn't design high-compression engines when no fuel existed to run them. Oil companies wouldn't invest millions in high-octane fuel production when no engines existed to use it. Classic chicken and egg problem. So Doolittle broke the deadlock. He convinced Shell to invest in developing 100-octane fuel, even though no market existed for it. The initial cost was staggering, $25 per gallon when automotive gasoline cost 20 cents. Shell executives called it Doolittle's million-dollar blunder. But Doolittle proved the concept through aviation racing. In 1932, flying a Gi-B racer with 100-octane fuel, he won the Thompson Trophy at an average speed of 252 miles per hour. The performance advantage was undeniable. Then he took his case to the military. The Army Air Corps in the 1930s operated on Depression-era budgets, spending money to develop new fuel specifications when existing fuel worked fine seemed wasteful. But Doolittle presented the strategic implications. Higher octane fuel meant more powerful engines without increased weight. More power meant better performance at high altitude, where combat would happen in the next war. Better high-altitude performance meant air superiority. The Army adopted 100 octane as the standard specification in 1938. Not because they had the fuel, because they wanted to force industry to produce it, and industry responded. By 1940, American refineries were producing 100 octane in sufficient quantities to supply the British Royal Air Force. This fuel, rated 100/130 octane, transformed the Battle of Britain. British fighters using 87 octane fuel in 1939 were outperformed by German fighters. Same British fighters using 130 octane fuel in 1940 matched or exceeded German performance. The Merlin engine, running on American fuel, developed enough power to make Spitfires and Hurricanes competitive with Messerschmitt 109s. The 130 octane fuel came from a specific refining process called catalytic cracking. The Houdry process, developed by French engineer Eugene Houdry and perfected by American oil companies. This process broke down heavy petroleum molecules into lighter, higher octane components. By 1944, 77 Houdry process plants across America were producing 400,000 gallons per day. But even as 130 octane became standard, researchers were pushing beyond. The British, perpetually short of petroleum and perpetually desperate for performance advantages, began testing even higher octane fuels in 1942 and 1943. The research focused on additives. Pure octane, the chemical compound from which the rating scale derives its name, has an octane rating of exactly 100. To go beyond 100 requires adding compounds that inhibit detonation better than pure octane. The primary additive was tetraethyl lead, a toxic organometallic compound that had been used in small quantities in fuel since the 1920s. Tetraethyl lead works by interfering with the chemical chain reactions that cause detonation. Tiny amounts, measured in grams per gallon, allow fuel to tolerate much higher compression ratios without knock. But there's a limit. Too much lead causes other problems: spark plug fouling, valve deposits, exhaust valve burning. The challenge was finding the maximum concentration that prevented detonation without destroying the engine through lead poisoning. British researchers at the Royal Aircraft Establishment and at Rolls-Royce experimental facilities ran systematic tests through 1943. They tested Spitfire 9s with progressively higher octane fuels. The results were documented with scientific precision. October 1943. Rolls-Royce tests a Spitfire 9 at Hucknall with experimental 150 octane fuel. Manifold pressure increases from 18 pounds per square inch to 25 pounds. Power output jumps from 1420 horsepower to 1700 horsepower. A 20% increase in power with no mechanical changes, just different fuel. November 1943. The Aircraft and Armament Experimental Establishment at Boscombe Down confirms the results. Their report concludes that 150 octane fuel provides significant performance advantages with acceptable engine wear rates. Meanwhile, across the Atlantic, the U.S. Army Air Forces Material Command is running parallel tests. January 1944. A conference at Wright Field brings together researchers from the National Advisory Committee for Aeronautics, engine manufacturers, and oil companies. The goal is to investigate 150 grade fuels and determine their military value. The conclusion is unambiguous. 150 octane fuel offers substantial performance gains for long-range patrol and bombardment operations. The fuel, designated P-44-1, should be produced and fielded as expeditiously as possible. But production was one thing, distribution was another. Manufacturing 150 octane fuel required even more complex refining processes than 130 octane. The tetraethyl lead content was higher, the chemical balance more delicate, the quality control more stringent. American refineries ramped up slowly through early 1944, initial production measured in thousands of gallons per month. By mid-year, production reached tens of thousands of gallons per month. Still nowhere near enough to supply the entire 8th Air Force. Then there was the shipping problem. Every gallon had to cross the Atlantic. German U-boats had been largely defeated by 1944, but the threat remained. Tankers carrying high-octane fuel were priority targets. Lose a tanker, and you lose not just the fuel but the specialized tanker itself, which took months to replace. Storage presented additional challenges. The 150-octane fuel degraded synthetic rubber, which meant every fuel line, every gasket, every seal that contacted the fuel needed to be replaced with compatible materials. Ground crews at English airfields received detailed instructions on handling, avoid skin contact, work in ventilated areas, replace fuel system components on shortened schedules, monitor for leaks obsessively. The color coding helped prevent mistakes. Standard 130-octane fuel was dyed green. The new 150-octane fuel was dyed purple. Distinctive, impossible to confuse, clearly marked on every storage tank and fuel truck. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. March 1944. The confluence of technologies finally aligns. P-51 Mustangs with 85-gallon fuselage tanks provide the range. 150-octane fuel provides the efficiency and power. External drop tanks, now standardized at 110 gallons each instead of the earlier 75-gallon versions, provide additional margin. The total fuel capacity reaches 489 gallons. Do the math. 489 gallons at 58 gallons per hour consumption equals 8.4 hours of flight time. At cruise speed of 300 miles per hour, that's 2,520 miles of theoretical range. Cut that in half for combat radius, accounting for takeoff, climb, combat reserves and landing, and you get 1,260 miles. Berlin is 662 miles from England. 1,260 miles of combat radius provides a cushion, not a large cushion, but enough. Enough to escort bombers to the target. Enough to engage German fighters en route. Enough to return to England with fuel remaining. The mission on March 4, 1944 proves the concept. Over Berlin, P-51 Mustangs from the 357th Fighter Group engage Luftwaffe fighters while bombers hit their targets. The psychological impact on German pilots is immediate and devastating. American fighters over Berlin, the capital of the Reich under attack with continuous fighter escort. The supposedly impregnable heart of Germany proven vulnerable. Losses among the bombers drop dramatically. German fighter tactics had depended on attacking after American escorts reached their fuel limits and turned for home. When the escorts stop turning for home, when they follow the bombers all the way to the target and all the way back, Luftwaffe losses start exceeding bomber losses. The strategic calculation shifts. Prior to long-range escort, German fighter pilots could pick their moments, attack from advantageous positions, break off when Allied fighters appeared, and return to base safely. After long-range escort arrives, every bomber raid becomes a fighter battle. The Luftwaffe has to engage Allied escorts, or let the bombers through. Either way, they're committing resources to battles they're increasingly losing. German fighter pilot training programs, already stressed by casualties and fuel shortages, can't replace experienced pilots fast enough. By mid-1944, average Luftwaffe fighter pilot experience has dropped below 100 hours. American and British fighter pilots often have 300 to 500 hours. The experience gap translates directly to combat effectiveness. The Mustang, with its combination of range, speed, and maneuverability, becomes the dominant fighter over Europe. By the end of 1944, 14 of the 8th Air Force's 15 fighter groups fly Mustangs. The 15th, the legendary 56th Fighter Group, stays with P-47 Thunderbolts out of pride and preference, but they're the exception. The 150-octane fuel remains in continuous use through the end of the war in Europe. An 8th Air Force technical memorandum from April 1945 summarizes the experience. Approximately 100 million gallons of 150-octane fuel consumed by fighter aircraft. Performance gains consistent across all types. P-51, P-47, and P-38 aircraft all benefit from increased power and improved efficiency. But the fuel comes with costs beyond the chemical composition. The lead content causes accelerated engine wear. Spark plugs foul more quickly. Exhaust valves burn faster. Engine overhaul intervals shorten from 200 hours to 150 hours. The maintenance burden increases, but the operational advantages outweigh the costs. Mechanics and crew chiefs learn to work with the fuel's peculiarities. Fuel system leaks become constant concerns. A P-51 that sits overnight with 150 octane in the tanks might develop seepage around fuel line connections as the fuel degrades rubber seals. Ground crews perform pre-flight inspections with heightened attention to fuel system integrity. Better to catch a leak on the ground than discover it at 25,000 feet over Germany. Pilots learn to respect the fuel's properties. The increased power available at war emergency settings is intoxicating. 75 inches of manifold pressure transforms the Mustang into a rocket, but using that power requires discipline. War emergency power is limited to 5 minutes maximum. Exceed that limit and you risk catastrophic engine failure. Cylinder head temperatures spike, internal components exceed design limits. The engine might hold together, or it might grenade, sending connecting rods through the crankcase and leaving you gliding toward whatever landing spot appears less fatal than the alternatives. The tactical employment evolves. Early missions see pilots using war emergency power liberally, burning fuel at 250 gallons per hour to chase German fighters. Then, someone does the calculation. 5 minutes at war, emergency power consumes 20 gallons. 20 gallons represents 60 miles of range. Trade speed for endurance or endurance for speed, depending on the tactical situation. Experienced pilots develop intuition for fuel management. They can feel when they're burning too much, when they need to throttle back, when they can afford to push. The fuel gauges provide data, but the seat of the pants provides wisdom. An aircraft that's been burning fuel at optimal cruise for 3 hours handles differently than one that's been dogfighting at full throttle. The weight difference is subtle, but perceptible. Navigation becomes critical in ways it wasn't for shorter-range missions. Running out of fuel 20 miles from England isn't a minor inconvenience. It's a death sentence. Pilots learn to navigate precisely, using landmarks, radio beacons, and dead reckoning to ensure they're tracking toward friendly territory with adequate fuel reserves. The North Sea remains unforgiving. Water temperature in March hovers around 40 degrees Fahrenheit. Immersion survival time measures 15 to 30 minutes before hypothermia incapacitation. Ditching procedures are taught, practiced, memorized. Unlatch the canopy before impact. Tighten harness. Brace. After impact, exit immediately. Inflate life vest. Deploy dinghy if you have one. Activate radio beacon. Wait for rescue that might never come. Air-sea rescue operations improve throughout 1944. Fast rescue boats patrol the channel. Spotter aircraft watch for downed pilots. Radio direction finding equipment helps locate distress signals. But even with improved rescue capabilities, ditching in the North Sea means long odds and cold comfort. So pilots guard their fuel like misers guard gold. Every gallon represents minutes of flight time, miles of range, options that might save your life. The difference between making it to England and ditching in the Channel might be 10 gallons. The difference between landing at your home field and diverting to an emergency strip might be 5 gallons. You manage fuel not just by the numbers on the gauge, but by the weight of responsibility to get yourself and potentially your wingmen home alive. The strategic impact of the P-51's extended range, enabled by the combination of fuselage tanks and high-octane fuel, resonates beyond individual missions. The bomber offensive against Germany, which seemed on the verge of failure in late 1943, succeeds spectacularly through 1944 and into 1945. German industrial production peaks in mid-1944, despite sustained bombing, a testament to German organizational efficiency and dispersal strategies. But the attrition of German fighter forces, forced to engage in constant battles with increasing numbers of Allied escorts, degrades Luftwaffe capability month by month. By the time of the Normandy invasion in June 1944, Allied air superiority over Western Europe is absolute. The Luftwaffe can barely contest the airspace over the invasion beaches. German ground forces fight without effective air support, while Allied air forces operate with impunity. The extended range of escort fighters also enables operations that would have been impossible earlier. Missions to southern Germany, to Austria, to Czechoslovakia all become routine. The oil facilities at Ploiesti, Romania, previously beyond range of Mediterranean-based fighters, come under escort by P-51 Mustangs flying from Italian bases. Every target in occupied Europe and Germany becomes vulnerable. The psychological effect on German military leadership is profound. The vaunted Luftwaffe, which had terrorized Europe in the early war years, is fought to exhaustion. The Jagdwaffe, the fighter arm, loses over 30,000 pilots killed between 1943 and 1945. The training pipeline cannot replace them. The fuel shortages prevent adequate training for replacement pilots. The spiral into defeat becomes irreversible. But on March 4, 1944, over Berlin, the pilots flying P-51 Mustangs with 85 gallons of fuel behind their seats and 150 octane in their tanks don't know they're making history. They know they're cold. They're scanning the sky for enemy fighters. They're watching fuel gauges and engine instruments, and they're hoping to survive the mission and return to England for interrogation, warm food, and the next mission briefing. The dangerous fuel, the toxic fuel, the fuel that eats rubber and requires special handling and causes accelerated engine wear, this fuel keeps them alive. It gives them range to reach targets that were previously beyond reach. It gives them efficiency to fight and return home. It gives them power to engage German fighters on equal or better terms. The 85-gallon fuselage tank, the modification that makes the aircraft dangerously unstable on takeoff, handles like a compromised pig for the first 30 minutes of flight and requires rigid fuel management discipline. This tank makes the missions possible. Without it, the P-51 remains a medium-range escort fighter, capable but not transformative. Together, the tank and the fuel create capability that didn't exist before. The capability to escort bombers anywhere in Europe, the capability to contest airspace over Germany itself, the capability to turn the tide of the air war. And it all comes down to fuel management. 330 pilots in P-51 Mustangs, each managing 489 gallons of fuel across multiple tanks with different handling characteristics, burning fuel at rates that vary from 58 gallons per hour at cruise to 250 gallons per hour at war, emergency power, navigating across 662 miles of occupied territory, fighting when necessary, conserving fuel when possible, and getting themselves home. No single mechanic mixed a dangerous fuel blend in a workshop and revolutionized air combat. That's Hollywood fiction. The reality is more complex and more impressive. The reality is systematic industrial development of high-octane fuels spanning years. Engineering compromises that trade stability for range, tactical procedures that manage dangerous configurations safely, pilots who master fuel management like accountants master ledgers. The reality is less dramatic in individual moments, but more dramatic in aggregate outcome. The air war over Europe turns not because of one invention, but because of multiple innovations converging. The Merlin engine with its efficient fuel consumption, the laminar flow wing with its low drag, the fuselage tank with its range extension, the 150-octane fuel with its power and efficiency, external drop tanks with their additional capacity, improved navigation equipment, better tactics, experienced pilots. Every component contributes. Remove any single component and the system fails. The P-51 without the Merlin engine remains a low-altitude fighter like the early Allison-powered versions. The Merlin engine without high-octane fuel produces adequate but not exceptional power. High-octane fuel without the fuselage tank extends range, but not enough for Berlin. The fuselage tank without proper procedures causes fatal accidents. Proper procedures without trained pilots result in confusion and errors. It's a system. A complex system where every part depends on every other part. And that system, fully realized in March 1944, changes warfare. The legacy of the P-51's extended range extends far beyond 1944. The principles established: fuel, management as critical skill, engineering compromises that accept limitations to gain capabilities, systematic integration of multiple technologies. These principles become foundational to military aviation. Modern fighter aircraft still carry fuel in configurations that compromise handling. The F-16 carries centerline tanks that affect stability. The 15 uses conformal fuel tanks that alter aerodynamics. Every designer faces the same trade-off the P-51 engineers faced: performance versus range, maneuverability versus endurance. The mathematics haven't changed. Only the numbers have gotten larger. High-octane fuel development didn't stop in 1945. The progression continued. 115/145 octane fuel-powered American aircraft through the Korean War and into the Vietnam era. Piston engines reached power outputs impossible with lower-grade fuels. The Wright R-3350 engine in the Ione Sky Raider, still flying. Combat missions in 1973, burned 115-octane fuel and produced 2,700 horsepower from 18 cylinders. But the real revolution came from what the P-51 proved strategically. Air superiority requires not just better aircraft, but sufficient range to contest airspace wherever combat occurs. The lesson seems obvious now. In 1943, it wasn't obvious at all. Conventional wisdom said fighters defended territory, intercepted bombers, fought near their bases. The P-51 demonstrated that fighters could project power, could escort bombers across entire countries, could achieve air superiority through presence rather than just performance. Every subsequent conflict validates this principle. Korea sees F-86 Sabres escorting B-29 bombers deep into North Korea. Vietnam sees 4 Phantoms, providing continuous cover for strike packages. Desert Storm sees 15 Eagles maintaining combat air patrols over Baghdad for weeks. The operational concept traces directly to March 1944 over Berlin. The engineers who added that 85-gallon fuselage tank never received medals. Their names don't appear in history books. The chemists who developed 150-octane fuel worked in industrial laboratories, published in technical journals, and moved on to post-war careers without recognition. The pilots who mastered the fuel management, who brought their aircraft home mission after mission, most of them survived the war and returned to civilian life without fanfare. But their work persists. Every time a modern fighter refuels in mid-air to extend range, that's the P-51's legacy. Every time a pilot manages fuel across multiple tanks to optimize performance, that's the training methodology established in 1944. Every time engineers compromise one capability to gain another, that's the design philosophy the Mustang proved viable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. The dangerous fuel wasn't really dangerous. The modifications weren't really mad scientist experiments. The revolution wasn't really revolutionary in the sense of happening overnight. It was systematic, methodical, engineering-driven development of capabilities that the war demanded. But the result changed everything. And that's the story nobody tells. The boring story of fuel management and engineering compromises that won the air war over Europe.